Okay. So this is the block diagram. Because block diagram means that what we call as schematic diagram. Schematic diagram. So it's not for you to understand the circuit or anything, but what you need to understand is that electrochemical technique in general is divided into two: potential, okay, potentiometric, and voltammetry. So what we're going to be discussing today is only voltammetry. So potentiometry is actually a very good technique. Actually, you commonly use in pH meter. So pH meter is an example of a potentiometric technique. Yeah. So this is voltammetry. So voltammetry, in which information about an analyte is obtained by measuring current. Yeah. So in electrochemical technique, of course, the name is electrode. So for specifically voltammetry, we are measuring current. So if you remember your secondary schools, electrochemistry, you have a galvanic cell, okay, and electrolytic cell, okay. That's very fundamental. So galvanic cell is when you mix together the chemicals, you get current automatically. So you get a flow of current. Yeah? So it means that the reaction happens spontaneously, producing current. So in the beaker, the redox reaction happens. So I hope that you remember the word reduction, oxidation. So in the beaker, the reduction and oxidation happens spontaneously, yeah? In galvanic cell, spontaneously, and then producing current. So that is the fundamental of potentiometry. So the other cell is electrolytic cell. So in electrolytic cell, the redox reaction does not happen spontaneously. It has to be induced, or it has to be, it needs external factor, which is it requires some potential. It requires some potential so that the chemical in the beaker can undergo reduction and oxidation. Okay, so that's what happened. I think this is the one that has been covered during your undergraduate, because this is something very basic, and even this is during the secondary school. Yeah, so what we're going to cover today is based on electrolytic cell. Yeah? Electrolytic cell means that it requires external potential, okay, so that the redox material, the chemicals inside the beaker, okay, try to remember the beaker, can undergo redox reaction. Yeah, reduction, oxidation. So reduction, oxidation, reduction, receive electron, oxidation, release electron. Yeah? Reduction, receive electron, oxidation, release electron. Yeah? So with that in mind, so after the reaction happen, again, you're going to get current. Okay, so the biggest difference with galvanic cell and electrolytic cell is electrolytic cell requires external force, external power, so that the reaction happen, because the reaction does not happen spontaneously. Yeah. All right. The other one is, okay, that is very important. Okay. So in voltammetry, or the basis is electrolytic cell just now. Okay. These are the most important parts. Working electrodes, reference electrode, counter electrode, and supporting electrolyte. Okay. So there are many different types of potential stat. This is what we call as potential stat. Okay, you can see here, which as I said just now, okay, the reaction requires external force or external power, so that whatever reaction in the beaker can happen. Okay, if no voltage supplied, there will be no reduction or oxidation happen. So once the reduction and oxidation happen in this beaker, so there is a flow of electron. Okay, so there is a flow of electron that, of course, producing current. Okay, so this is the current that we measure. Okay, external force causing the redox reaction, and then current produced. All right. Okay, so working electrode is where the main reaction happens. Okay, reference electrode, okay, is to control the baseline. Yeah. So if without reference electrode, the reaction can happen. The current can also be detected, but the baseline is not going to be stable. Okay, so that's why we need a reference electrode, because that the reference should have a constant potential. So potential remain constant. Yeah, so that we are going to have a good baseline, and we can measure the current. Okay, counter electrode. Okay, the purpose of counter electrode is to complete the circuit. So you can see that it is to complete the circuit. Okay, conduct electron from signal source through solution to the working electrode. So this is to complete the circuit. So it's not really important. Not to say it's not important, of course, but in terms of material, as long as it is a conducting material, then it can be a counter electrode. Yeah. Supporting electrolyte. Okay, again, I am sure that this is something that you have gone through. Some of you probably. Okay, is electrolyte requires so that the electron, the ions inside the beaker can move. Yeah, can move, because if there is too many resistance in the beaker, then the reaction or the movement of ions is difficult. So that's why we need supporting electrolyte. Excess of non-reactive. Okay, of course it has to be non-reactive, because we do not want the electrolyte to interfere with the main reaction. Yeah? Okay, so these are the most important. So you can see now it's sort of separate one, yeah? But now it's actually all in one single electrode. Yeah? All this working, reference, and counter all in one single electrode. Okay. Okay. So this one, we do not want to learn about potentiometry, but this is just to highlight just now when voltammetry focus on measuring current. Yeah. We do not need to discuss about coulometry, because we only want to discuss voltammetry today. So not too much lah. Yeah? Okay. So as you can see, focus here, the electrochemical or the voltammetry technique requires external force, which is the potential, right? The potential. So you can see the current produced, okay, from the reaction is according to this graph. The current changes is not linear. It's not linear. So it's sort of sigmoidal graph. So we will learn about this. Okay, what happened at the beginning, and what happened about in the middle, and what happened when the current sort of achieves saturation. Yeah. So so this is actually a nurse equation. Okay, nurse equation. So this depends. Okay, reaction at the surface of the electrode. We are talking about the working electrode. Yeah? Okay, just bear with me. We are talking about working electrode. Okay, so try your best to imagine now that in the beaker, okay, in the beaker there is ferrum 3+. Okay, so ferrum 3+ solution, okay, reduce, okay, as I said just now, reduction, receive electron, yeah, okay. So the ferrum 3+ is being reduced to ferrum 2+. When a specific potential is given, is given to the system, okay. So you can see that, let's say the potential is 30 millivolt, let's say 30 millivolts. Then if you give the system only 10 millivolt, then this reaction will not happen. Okay, so the applied potential is sort of specific to different redox reaction. So in short, let's say the reduction of ferrum 3+ to ferrum 2+ requires 30 millivolt, let's say. Then if you give 10 millivolt, then this reduction will not happen. So now you can see this graph, okay, showing the concentration of ferrum, okay, reducing against time, because against time that the ferrum 2+ will be converted into ferrum 2+. Yeah, okay, so this is against the distance. Okay, this one is not for you to worry. Okay, we'll show you what happened. This is what happened at the surface of electrode. You have to imagine that the ions in the beaker is not really, the movement of the ions is not the same at the time. It does not have the same type of movement all the time. Okay, it depends on the range or how far the ions from the electrode. Okay, so you have three transport mechanism: migration, convection, and diffusion. Yeah, so this is not for you to memorize, because this is for your understanding, to be able to understand the lab next week. Yeah, so this is what happened in the beaker. So the redox species just now, ferrum 3+, converted to ferrum 2+. So they have different types of dynamic. Yeah, the flow, how they flow, is not similar, and depends on the how far, okay, or just now we distance from electrode. Okay, right. So in short, in simple, this is what we can imagine, that this is the beaker where the redox reaction happen, and then you have working, okay, working electrode. Okay, in this case it is platinum. Okay, and then you have reference electrode, okay, SCE, standard calomel electrode. If you want to Google standard calomel electrode, okay, so this is the reference, and this is the counter. So in this case, in this slide, we are using argentum, okay, as the counter electrode. Okay, so you can see here. Okay, so if you remember the standard redox, okay, potential for plumbum to be reduced to from plumbum 2+ to plumbum is negative 0.13 volts, and for potassium plus to potassium, the redox potential is to negative 2.93. So this one is not for you to really worry about. But this is sort of what is happening. For example, next week we are going to detect heavy metals. Yeah. Okay. Right. Okay. So you can see that in the beaker there are many. In this case, we are focusing on potassium plus and Pb2 plus. So we have a lot of ions moving inside the beaker. Okay. Okay. So this is a sort of a process what is happening inside the beaker. Okay, concentration gradient created between the surrounding and the electrode in the bulk solution. Okay, stop the migration of PB. Okay, this is a very basic, not to say very basic, this is very fundamental on how or what is happening on the surface of electrode. So let's say you want to identify only, okay, let's say in beaker we have Pb2 plus and K plus, potassium plus and Pb2 plus, but you wish to identify only K plus. So we need to give the right potential to the system so that only K plus will be absorbed or actually moving towards the electrode. So you can see that layers of K plus. Okay, this one, let's finish it. Okay. All right. I'm gonna show you what happened. Apply potential. This is a bit detailed. Okay. You can see that in this case, we are detecting cadmium 2 plus with potassium nitrate supporting electrolyte. So let's look at what happened during the time. Okay, so when we run the analysis, okay, so you can see here, so these are the potential force. So these are the voltage that we apply to the system. So previously I have mentioned that in order for cadmium 2 plus here to be reduced to cadmium, okay, it requires external force, which is in the form of potential. So you can see that starting 0.2, negative 0.4 potential until negative 0.6, okay. So this is slightly the current start to be observed. As you can start to observe current starting from, I can say around negative 0.5. Means that this is when the reduction of cadmium 2 plus to cadmium, the reduction of cadmium 2 plus to start to happen. Okay, so I mentioned just now, if you give the wrong potential, in this case, if you just focus on negative 0.2, then this reaction will not happen. But you can see that starting from here, the reactions start to happen, the redox start to happen, and then we are going to observe current, significant current, right? Okay, so this is what happened. Remember that I told you that the sigmoid, so sigmoid curve, okay. So from the beginning, there is no current. We call it residual current, means that the current is not due to the redox reaction. It might be due to electron movement inside the beaker, it's not significant. But starting from here, now the current is due to reduction of cadmium 2+ to cadmium. And then when it is sort of constant, you can see that it's actually constant, means that all the cadmium 2+ in the beaker is already reduced to cadmium. Okay, so when it is all the species, the redox species, cadmium 2+ has been converted to cadmium, then there's no more current. Okay, because all has been converted into cadmium in elemental form, then there is no more what we call as redox species to be that can undergo a reaction. Okay, redox reaction. So this is what happened. The most important that you need to understand before you can run the potential stat next week. Okay, everybody will have chance to run the potential stat. Yeah. All right. Okay. So this is this potential. You can see that if we run the potential stat and then obtain this voltammetry voltammogram, okay, voltammogram, we can identify what we call as E half, yeah, half potential. Yeah? So this one, what is actually E half? Okay. If any, I'm sure that some of you is very familiar with chromatography. So for chromatography, for you to identify the species, you need to base on RT, retention time, right? So the retention time is like a unique fingerprint, unique fingerprint for the species. So for voltammetry, E half, E half is like VRT, it's like retention time in chromatography. It sort of represents the species itself. Okay, so all electrochemical active species, they have their specific. It's not really too specific, but they have this range of potential that they can be reduced or oxidized. So this is how we obtain the E half. Okay, so in short, the E half is for qualitative, mean we can identify, okay, it is cadmium. Okay, but the ID baseline of residual current, so this is where the residual current from here, so we can measure into up to the maximum. So this ID current, okay, represent the concentration. Okay, so it can be qualitative, we can identify from E half, and it can be calculated quantitatively by using this current. So that's why this technique is good, because it's like chromatography, you can identify based on the retention time, and at the same time you can calculate the concentration of that analyte based on the peak area. So this one, the E half represent the qualitative, the watt, and the current represent the quantitative, or how much it is in the beaker. Okay, so that's most important. So this one is called limiting current. Here is residual current, and this is limiting current. All right. So it also can identify more than one species. So let's say you have a mixture of more than one analytes. So we can observe actually more than one E half. So here you can see that there is a different E half here. two or more species are observed in the Voltammogram if difference in separate half-wave potential. E half, it is half-wave potentials are sufficient. Okay, so electrochemical technique can be used to analyze a mixture of aldolites. Okay, this one, all right. Okay, I'll be showing you examples, some of the Voltammogram. Okay, so under Voltammetry, there are quite a number of techniques. Even under Voltammetry itself, it has quite a number of techniques. So one of it, the most basic is Voltammogram. So this is called cyclic Voltammogram. Why is it cyclic? Because it's if that species reversible, it can go reduction, oxidation, reduction, oxidation. Yeah, so that's why it is cyclic. It can go, it can be reduced, and it can be oxidized back. Okay. All right. So in detail, what happened? So we can identify the process one by one, but this is not very important for you. Okay. Let's okay. So I think this one is done. Okay. So I'll be showing you an example of the actual TPV, but this is not based on metal. Okay, this is example of potentiostat. So potentiostat, the size is now getting very small. So it's very, what we call as robust. It has many techniques, but the size become smaller, which is actually very good. Instead of like, if you have to do chromatography, then the instrument is still big in size. We still do not have a small chromatography, but this one it is much smaller than even you can get in the size of handphone. This one, okay, this is example of our potentiostats. Okay, I just skip this. Okay, so you can see that the one that I mentioned just now, we have potentiometry and we have voltammetry. Okay, so this is the basic one, the basic one that we used to have long time ago. We have a beaker, we have counter electrodes, we have working electrode and reference electrode. Yeah, so we actually no longer use this type. Yeah, so right now we are using this, and I told you it is all in one. Previously is separate working, counter, and reference. Now everything is in one single electrode, counter, working, and reference electrode. Yeah, so reference electrode usually is it is called AgCl, argentum chloride. So this is actually small, very small. It is half. Okay, you will see it next week. Okay, all right. This one I have explained just now. And this is the process that is happening on top on the electrodes. Okay, so this is the electrode, and then when you have a species, remember the cadmium just now. Okay, so try to remember the cadmium. So the cadmium has to move. The cadmium ion has to move here before it can be reduced. It cannot be like so far here, it cannot be reduced. So there is, that's why we need to use supporting electrolytes, because that's the one that sort of helps the the cadmium ion just now to move closer to the electrode, and that's when the cadmium can be reduced. Yeah. All right. So these are some factors: mass transfer, electron transfer. Okay. Right. So you can see these are the when we do experiment, we have to like optimize these factors. Yeah. Among the factor is the supporting electrolyte. Okay, because different supporting electrolyte is suitable for different analytes. So we have to optimize that. And the other one, usually we focus on the surface of electrode. Okay, whether we need to sort of improve the surface area or add some nanomaterials so that the conducting capability of the electrode is much better. So for your physical lab next week, we are going to modify the electrode with gold nanoparticle, so that the current can be enhanced. With higher current, then the detection can be much sensitive. Yeah? So this one, I think I have shown you just now. So you do not need to worry, but these are some of the factors that will affect the reading of electrochemistry. All right, so let me, so this one is for those. I just want to show the example of DPV. Right, hopefully we have it. Okay. It's not a nice example. Okay. Right. So you can see the size of the electrode is very small. Okay. This slide is actually for those who are taking sensor technology. So, okay. I do not have a nice CV or DPV here, but this is the one that you are going to do next week. You are going to detect a series of metals, metal ions. So you can see that this is cadmium and this is plumbum, right? So if you remember just now, I mentioned about the potential. So cadmium and plumbum can be differentiated, can be detected using, because the reduction peak, okay, this is the reduction peak, will appear at different potential. So that's how we get different peak for different species. Yeah. So that's one thing, okay, about electrochemical technique, that you sort of retention time, yeah, just like retention time. So based on the retention time, you can identify the species. So in this case, the voltage is different for these different two species, cadmium and plumbum. Okay, and I just would like to share that electrochemical technique is very robust. Okay, you can see that our group has done a lot on DNA sensor, immuno-based sensor, which is based on electrochemical technique. So this is very robust technique that you can probably wish to explore if you wish to do a PhD, or if you wish to do R&D at your workplace. So this is very robust technique and very useful if you want to apply for your next level. Okay, and next one, okay, I would like to discuss on the module itself. Okay. Okay. So for electrochemical, it requires actually a whole one course itself to learn about electrochemical technique. So it's impossible to discuss it in 1 hour. So I just want to give you an idea because it's a very useful technique. So I hope that you can explore in future. So this is going to be your experiment next week. Okay, determination of trace metals means because metals usually in very low concentration. Yeah, I don't know whether I don't think we are using sewage. Yeah, we are using standard standard solution that we are going to prepare next week. All right, using electrochemical technique. So the purpose of the next week, the experiment, okay, is of course, one is to modify the electrode. Remember that I mentioned that we can modify the surface of the electrode in order to increase the conduction, in order to increase the current. That's the purpose of modifying the electrode. So you will be using screen printed carbon electrode. The picture that I have shown just now, the 3-in-1 electrode, and you'll be using gold nanoparticles. And after that, you'll be using the modified electrode to detect, okay, to look at the current by detecting plumberm 2+, cadmium 2+, copper 2+, and zinc 2+. Yeah? So you'll be using a differential pulse anodic stripping voltammetry. So don't worry, okay. This is one of the technique under voltammetry. This is one, as I said just now, if you observe, there is cyclic voltammetry. So this is one of the technique, differential pulse voltammetry. Okay. Right. So what, of course, you need to have introduction, objective. So it is there already, the objective and the introduction. You can add a bit based on the fundamentals that we learned just now. But in procedure, as you can see, there is no mentioning about how to prepare the gold nanoparticle. So after this, you need to find out on the preparation of gold nanoparticle. Yeah? So do not try to use a very complicated. Yeah? Of course, this one will be, as I said, when you do the physical lab next week, probably you need to amend the method that you propose for this week, because based on what we have in the lab. Okay, but I would like to see whatever that you propose for the preparation of the gold nanoparticle. Yeah, so do not use some complicated procedures, okay, because it's quite easy to prepare the gold nanoparticle. And the working electrode of SPCE was modified with 10 microliters of gold nanoparticles. So you need to detail out these two. Yeah? The first one is quite easy. I mean, it's straightforward. Yeah? Pre-treated using CV technique in 0. Okay, this one is quite easy. So I want you to focus on step 2 and step 3 to detail out. Yeah. All right. So the technique will be this one, differential pulse anodic stripping voltammetry. So why anodic stripping? Of course, we do not learn about that in this class, but is stripping, the word itself says stripping, means that it strips the ions from the solution so that it is concentrated on the surface of the electrode. Yeah, that is stripping. Okay, and the second one that I would like you to detail out is preparation of the standard solution. Okay, so you just suggest what salts that you need to prepare, dissolve, so that you prepare 0.1, 0.5, and 1 ppm. Okay, so this is like using your fundamental bag, whatever that you have learned for standard solution preparation. Yeah, so right, so the subsequent. Okay, the next one that I would like you to detail out is preparation of ferrum cyanide. Ferrum cyanide. Ferrocyanide. Okay, so find out on how preparation of ferro and ferricyanide. This one you can obtain from journals. If you can find open resource journal on electrochemistry, do not find the complicated one, find the simple one. Then there's a lot of mentioning about ferrocyanide. So you can see that it's not much that you need to add up into your method section. What you need to identify or detail out is the one that I put in red font. Okay, so in terms of introduction, you can add some more, the fundamental, the theory, and the procedures. Only add on, detail out the red font. Okay, the objective still the same. Okay, chemical reagents you can add up based on once you identify the detail, so you can put the detail in here. What are the things is required? So in method section, you can also put figures. Figures. All right. Yeah, questions.
Prof, when we should submit this thing, Prof? Today?
Okay, as I said, the first part I suggested. Okay, the first part you should have introduction, objective, and just now is the method. So I don't know whether, okay, how long do you need? How long do you need?
By Tuesday, can Prof?
Tuesday is fine. Yeah, for me it's fine. Everybody agree on Tuesday, or if you want to submit earlier, it's fine. I will yeah, put in Putra Blast if it is okay. If it is not okay, then I will put in MS Teams, the assignment, so that you can upload the first part of your report. So is everybody okay on Tuesday? Tuesday, right?
Yes,
You mentioned. Or you want more time? Because I plan to put you in groups after this. Okay, so that you can have a proper session with your partner to find out all the things. And then probably we regroup to have any discussion if you have any problem. Probably another half an hour before your session end, we regroup, and then you can ask me questions on your methodology probably. Okay, right.
Prof, you will the correction, if let's say got any correction, you will feedback to us before the lab section, is it?
No, during the lab session, because in the lab session is when we That's why I need you sort of to ask to show to me, okay, your method section, not too detailed, but at least to show to me, present to me this one, the method section, so I can say, okay, this is okay, this is too complicated or not. But there's still amendment. There is still amendment once the physical lab next week, because we will show you the actual methodology and all that. Some of the methods might be different, but the purpose today is for you to find out. But it's not exactly going to be conducted using your proposed method today. I hope they understand. The first part is for B2 marks. So even though it's not going to be the same thing that be conducted in the physical lab, of course there will be amendments. So it's not going to be a big difference. You just change some chemicals, the amount of the chemicals. Okay. So before you submit the whole complete report after the physical lab. We try our best for this session. The first module is always difficult, but then after that it's gonna be okay. So what I'm gonna do today, now, not today, is to divide you. Okay, so before I divide you into groups, is there any questions?
Prof, later we